You're watching a Channel 98 NBISD TV production.
Hey, welcome to another edition of That Geometry Show. As always, I'm your host, Kevin Corpy. And if you're wondering why I'm dressed up like this or why I'm out here on location in Lake Tahoe, not really, well, it's for a very good reason. You see, today's lesson is on my very favorite math concept in the whole wide world. We're going to be talking about slope today. So I thought we'd come out here on location and do a little skiing, okay? You up for that? Well, I want you to go out there and grab your ski bibs, grab your ski goggles, and your pencil, of course, and download those worksheets from the district website at www.newbraunfels.txed.net, and we'll hit the slopes. All right, lesson 6 is going to correspond with your Glencoe Geometry chapter 3.1 and 3.2. Of course, you know it's slope. Now, by the end of the lesson, you should be able to, number 1, find the slopes of lines. Number 2, know the slopes of two special types of lines and why the slopes are such. Number 3, determine if two lines are parallel, perpendicular, or neither parallel and perpendicular. And number 4, we're going to build a ramp in accordance with the American with Disabilities Act passed in 1990. So those ski goggles are going to double as construction safety goggles. All right. Now, if you've ever skied, you've probably thought about the steepness of the slope. Well, in math, we use the word slope to describe the steepness of a line in the coordinate plane. And we talked about the coordinate plane on a previous episode. Slope can be described as the ratio that describes the steepness of the graph, and it measures basically how fast the graph rises with respect to how fast it runs. Okay, you've all heard rise over run. Well, we can also think of it as the average rate of change between 2 points. Now let's call those 2 points x sub 1, y sub 1, and x sub 2, y sub 2. Now that we have those 2 points, we can describe it as in a precise mathematical definition. So here we go. Slope is equal to a lot of things. Slope is equal to, we use the letter m. And I'll talk about why the letter m here in just a second. But slope is m, and it's y sub 2 minus y sub 1. That's going to be the change in your y values, the change in the rise, over the x sub 2 minus x sub 1, the change in your x values, or the change in the run. Now from Algebra 1, you're used to it as just being rise over run. Here's another symbol we've used on a previous show, the little delta. It's a triangle symbol. That means change in. So you could think of slope as the change in the y values divided by or over the change in the x values. And because we have variables in the denominator, we don't want in this case delta x to ever equal 0. Bad things happen when we divide by 0, and we'll get a chance to do that later on in this episode. So when we take the slope, we're basically measuring the change in the vertical with respect to the change in the horizontal. Okay, so vertical is rise and horizontal is run. Now, why the letter m? Okay, if you've in algebra, you remember y equals mx plus b, where m was the slope. Why m? That's a great question. Here's the answer. The French verb for to climb or to mount is the verb monter. Pardon my French there. Hey, and if you notice, monter starts with the letter m. So we get it from the French verb. So not only did they bring us the French fries, they brought us the letter for slope. Thanks, France. Okay. Let's actually hit the slopes. Woohoo! Let's start off by looking at this graph here. You can see the line. We want to calculate the slope of that line. Well, from the formula, we're going to need 2 points. So I'm going to choose some convenient points here that intersect the graph at a nice location. Any 2 points will work. I'm going to choose this point here. That's the point 4, 5, if you remember from a previous episode how to do that. And I need another point. This one looks good right here, the point 2, 4. Now that I've chosen my 2 points, I can use the formula. M is equal to the change in the y values. It doesn't matter which point I start with. I have a habit of starting with the second one. So I'm going to go 4 minus 5. That's the change in my 2 y coordinates, divided by the change in the corresponding x values. If I start with this ordered pair for the numerator, I've got to start with that ordered pair for the denominator. So that'll be 2 minus 4. Now all we have to do is simplify the numerator to the denominator. 4 minus 5, that's negative 1. 2 minus 4 is negative 2. Negative divided by negative is positive, so the slope is 1/2. Now again, what that means is I'm rising 1 unit for every 2 that I'm running. Let's go back to the graph. If I start at any point on the graph, and I'll start at this point here, the slope says all I have to do is go up 1 unit and right or run 2 units to get back onto the graph. Now it's worth noting here also, I got the slope of negative 1 over negative 2. I could have started at the same point, but now negative is in the down direction. I could have risen in the negative direction, negative 1, and run in the negative direction, which to the left, 2 units. And notice I end right back up on the exact same graph. Now, it doesn't really matter that I chose those 2 points. Let me choose 2 different points. I'll choose this point down here, negative 4, positive 1. And how about this point that's on the y-axis, 0, 3. Now, if I use the slope formula, I should get the same answer. Let's try it. Now, again, just to be crazy here, I'm going to start with the first ordered pair. So I'm going to do 1 minus 3 divided by the corresponding x value, negative 4 minus 0. Negative 4 minus 0. Now I'll just simplify. 1 minus 3 is negative 2. Negative 4 minus 0 is negative 4. And negative 2 negative fourths simplifies to 1/2, the exact same slope that we had. And again, I can start at this point and go up 1 over 2. I can keep going up 1 over 2. And I basically can get to any other point of the graph. Now notice that this graph had a slope that was positive. The slope was positive. We always read a graph like we read a book, from cover to cover. No, not really, just teasing. We read it from left to right, like we read the pages in a book. So if we look at this graph and we start on the left and go to the right, notice that your slope is rising from left to right. We say it's increasing. And any function that's increasing or rising from left to right is going to have a positive slope. Now, if we were skiing this graph from left to right, that would be quite a lot of work. We'd have to basically ski uphill. And unless we're training for something, it's much more fun to ski downhill. Okay? So graphs are a little bit different. We ski from left to right all the time. Well, let's try it again for this graph. Again, I have a graph. We read it from left to right. This graph is falling from left to right. So we say it's decreasing. You would anticipate then that the slope is going to be, yeah, if you said it out there, you said negative, you'd be right. Okay? Let's go ahead and verify that it's negative by taking 2 points and calculating the slope. Again, I just need any 2 points. I'll choose this one here that crosses at a nice point. That's going to be negative 2, positive 4. And what the heck, I'll cross over here and get one way down here, 2, negative 4. So any 2 points will work. Now the slope, m, is going to be the change in the y's. So I'll start with the second pair, negative 4 minus 4 over the corresponding x values difference, 2 minus, now be careful here, I'm subtracting always, and my other point is a negative 2. Subtracting a negative. So in the numerator I have negative 8 over 2 minus negative 2 is really 2 plus 2, which is 4, and negative 8 divided by 4 is negative 2. Now notice here we've kind of lost the fact that we have a ratio. You can always take any number and put it over 1 and not change the problem. So if you want to think about it as a ratio of slope, of rise to run, just put it over 1. And now you have your vertical and horizontal. Let's go ahead and try it out. Rising by negative 2. Well, that means rising in the negative direction. That's falling. That's going down. So I'll go down 1, 2 units from my original point, and I'm going to run 1 unit. Gets me back there. Now, because the ratio is negative, that's going to give us the same answer if we would have written it as 2 over negative 1. Now I'm actually rising 2 units and running in the negative direction. So let's pick any other point on the graph. How about that one? Now let's go ahead and go up 2. That's rising 2. And running in the negative direction is 1 unit to the left. So that's negative 1. We get right back on the graph. So if the slope is negative, then the numerator or the denominator can be negative. Okay, let's go ahead and summarize what we've already been doing here. A line, oh, did you notice about the last 2 examples? I'm sorry. We always read a graph from left to right. I've already talked about that, but we'll review. We read a graph from left to right like a page in a book. Okay? Once we establish that as a habit, then any graph that rises from left to right will have a positive slope, or a positive slope will rise from left to right, and any graph with a negative slope will fall from left to right. Got it? Okay, now you might hear your geometry teacher or anybody talk about the steepness of a graph. Now steepness is a little bit different, not much, but a little bit different than the actual slope. When we talk about the steepness of a line, we're talking about the absolute value of the slope. In other words, we don't care if it's rising or falling, if it's increasing or decreasing. Remember the symbol for absolute value. It's these two vertical bars. We could say steepness equals the absolute value of slope. So if I had one line that had a slope of 1, let's say, and another line that had a slope of -1, the first one here is increasing or rising from left to right. The second one is decreasing from left to right. But if you take the absolute value of both of those, you get 1. So they have the exact same steepness. They're just kind of going in opposite directions. Okay? Steepness versus slope. Slope is kind of directional and steepness is not. Okay, now back to skiing. What if you're a novice skier? What if you're just learning how to ski? Or what if you're a purple penguin, like the guy I have here? What slope would you prefer to learn on? You wouldn't want to hit the black slopes, which are really steep right away. You would probably want to learn to stand up on your skis first. And it's best to learn to stand on a flat slope or a horizontal line, like this little purple penguin right here. Let's go ahead and calculate the slope of this horizontal line. Again, I need 2 points. So let's zoom in. I'm going to show you the points. Any two will do. I'm going to choose the point -2, -1. So I'll write that over here. -2, -1. And I need one more. How about way over here? This looks like it's 1, 2, 3, 4, 5, -1. Okay, so 5, -1, and -2, -1. Let's go ahead and calculate the slope. M is going to be the change in the y's, so -1 minus -1, all over the corresponding change in x's, 5 minus -2. Well, look what happens in the numerator. That's really -1 plus 1, which is 0 over 5 plus 2 is 7. Now, 0 divided by any non-zero number is, in fact, 0. So we say the slope is 0. Okay? That's the best kind of slope to learn to ski on, a 0 slope or a horizontal line. Okay? Now, let's kind of look at the equation. Remember, it was delta y over delta x, which means change in. On a horizontal line, your y values are not changing. They're consistent. The x values can be anything. So delta y equals 0 on a horizontal line. Delta y meaning the change in y. They're not changing. And that's why your numerator is 0. Okay, now what about vertical lines? What if you are an experienced skier and you're crazy? A 0 slope is way too boring for you. Well, could you ski down a vertical slope? Unfortunately, you can try, but you're not going to be successful because it's not called skiing. It's called free falling, people. Okay? Be careful. And I'll show you why you can't ski down a vertical slope, because you can only ski down slope. Otherwise, it's total gravity working. All right, let's look at our purple penguin again. Notice the vertical slope, and look, he's a little bit apprehensive there. He shouldn't have done it. Let's find 2 points. Any two will do. This is at -1, -2, so I'll look at -2, 3, and another one, -2, -3. So the slope then, m, is equal to the change in the y values, -3 minus 3, over the change in the corresponding x values, -2 minus -2. Well, -3 minus -3, that's -6. -2 minus -2 is really -2 plus 2. That's a 0 pair. That gives us 0 in the denominator. That, my friends, is pretty dangerous. You cannot divide by 0. Bad things happen when you divide by 0. Okay, just like skiing down a vertical line, bad things can happen. This, we say, is undefined. Or there is no slope. No slope at all. It doesn't even exist. You can't ski down it. Okay, so we got to be very careful. 0 in the numerator divided by non-zero is 0. But 0 in the denominator is pretty bad. Okay, now we're going to summarize. These are the 2 special lines. A horizontal line has 0 slope, and a vertical line has no slope. And I'll show you quickly how you can remember that. 0, if you make 2 horizontal lines like this right here, make that into a z by connecting the diagonals. And then write ERO after it. There you go. So the Z in 0 is made up of two horizontal lines. So horizontal line has 0 slope. Now, vertical slope, if you make two vertical lines, okay, vertical line, now make an N out of it by drawing your diagonal and write the letter O after it. Now you have no slope. So vertical lines here have no slope. Whew! I'm ready for a break. How about you? Let's go watch some of those public service announcements, and we'll be back before the snow melts.
Yesterday, my friends told me to smoke some weed, and I did. Then today, they said I should try to outrun Tick-Tick, the little lumberyard dog. And I don't think I can. I'm an idiot. I'm doing stupid stuff, and that ain't me.
Live above the influence. Above them, above weed.
Hey, welcome back. You know, I think we have time for about one more run before we lose some daylight. What do you say we get right back to it? All right, so all this talk of slope has been good, but that's pretty much just been algebra so far. So you're probably asking yourself, where does all the geometry come in? Well, what we've actually been doing is something called analytic geometry. And it's due to this guy right here, a 17th century mathematician we've already talked about, René Descartes. He's the guy who came up with the coordinate plane. Remember he was watching the spider move on the wall? He's the guy that basically blended algebra and geometry, planar geometry, and brought it all to the coordinate plane. So what we've really been doing has been a special type of geometry, analytic geometry. So 1, 2, 3, let's thank him. Thanks, René Descartes. Okay, all right. Now, let's actually get to the actual geometry like you're going to be doing in class. Here are some VIPs, some very important postulates. And remember, those are the if and only if statements like we talked about previously. Here's the first one. Kind of hard to read, I apologize. It says, two non-vertical lines have the same slope if and only if they are parallel. Remember, we can reverse that and we could say two non-vertical lines are parallel if and only if they have the same slope. Now remember, we have to say non-vertical because if we include vertical, the slope doesn't exist. So here's what we can basically say. Parallel lines, parallel, double-headed arrow implies same slope. Or same slope implies parallel. Very important. The next postulate. Two non-vertical lines are perpendicular if and only if the product of their slopes is -1. Okay? Now remember, perpendicular lines intersect at 90 degrees, and we use this little symbol for perpendicular. So let's come up with two slopes. Let's talk about a slope M and its perpendicular slope, which I'm going to call M subscript with a little perpendicular sign. That means they're related. This one's a slope and that one's perpendicular to it. What this postulate says is if I multiply them together, I should get the number -1 every single time. Now, there's a more useful way to think about this. If we take this little equation now and solve it for M sub perpendicular, all we have to do is divide by M. So I get -1 over M. And this is a little bit more useful. We could then say that perpendicular slopes are, we can just say opposite reciprocals. All we have to do is if we have one of the slopes, flip it essentially, that's the reciprocal part, and change the sign. Opposite reciprocals. If you multiply two opposite reciprocals together, you're going to get -1 every time. That's a little bit easier to remember. All right, let's look at an example here. Point A and point B are on the same line. If the slope of the line is 3 over 2, 3/2, find the value of n. Well, here's my 2 points. Let's go ahead and set up my slope formula. Slope, m, is going to be the change in the y values, 4 minus -5 over 2 minus n. Now, I happen to know in this case that that number has to be 3/2, so I can set it equal to 3/2. And what I've done now is I've set up a little proportion here. So if I simplify, I get 4 plus 5 is 9 over 2 minus n, and that equals 3/2. Now, remember how to solve proportions in algebra? We cross multiply. So I get 9 times 2, that's 18, equals 3 times 2 minus n. And now I distribute the right side. That's 6 minus 3n. I will subtract 6. 18 minus 6, that's 12, equals -3n. And then dividing both sides by -3, I get 12 divided by -3, which is -4. So a little bit of algebra there, but we're using the slope formula to set up our equation. So the other point was actually -4, -5. And those 2 points now will have a slope of 3/2. Pretty easy, right? All right, let's move along. Find the slope of a line that is perpendicular. Remember, negative opposite reciprocals to the line that passes through the line that contains these 2 points. All right, so what do I need to do? This is kind of a strategy problem. We need to think in advance. I need to find a slope that's perpendicular to the line that passes through these 2 points. Well, I could find the slope of that line by using my slope formula. Once I have that slope, then I'll be able to obtain the perpendicular slope from it. So let's do that. M, the slope between these 2 points, again, change in y values, 2 minus -2, over the change in the corresponding x values, 3 minus 1. So that's going to be 4 over 2, which is 2. So if the slope is 2, or 2 over 1, how do I generate its negative reciprocal or opposite reciprocal? I'll call that m sub perpendicular to show that they're related. And all I have to do is flip 2 over 1 to get 1 over 2. And since it's positive now, it will become negative. And so that would be the slope of the line perpendicular to it. Now we can quickly check based on the postulate. The postulate says if I multiply the 2 slopes together, I should get -1. Well, let's try it. The slope that I found was 2, or 2 over 1. If I multiply it by my perpendicular slope, -1/2, the product of a positive and negative is negative, and the 2's divide out and the 1's divide out, leaving me 1. So there you go. You know you've got the right answer. Okay, building up in complexity. Another example. We need to find the value of x so that the line that passes through these 2 points is parallel to the line that passes through those 2 points. Oh, well, let's think about that postulate. It said if 2 lines are parallel, then their slopes are the same or equal. So I can find the slope of this line and the slope of that line by my formula and set them equal to each other. I think we'll do that. So I'm going to call the slope of the first guy m sub 1. We use a lot of subscripts. That's going to be the first line. So that's -3 minus 6 over 10 minus x. That has to equal the other slope, which is 11 minus 2, all over 6 minus 7. And that's going to equal m2. Well, really, the middle part is what I'm interested in, setting their slopes equal to each other. So let me go ahead and work it out now. I've set up another proportion. Simplifying in the top, I get -9 over 10 minus x, and that equals 11 minus 2. That's 9 over -1. All right, now I cross multiply. -9 times -1 is 9, and I get 9 times 10 minus x. Now I'll distribute on the right-hand side. 9 equals 90 minus 9x. Subtracting 90, I get 9 minus 90, which is -81, equaling -9x. And finally, dividing both sides by -9, I get -81 divided by -9, which is +9. And we found it. So that original ordered pair was the point 96 combined with 10 -3. Okay? Back up here. And I can be confident now from my algebra that my answer is correct and that those 2 lines are parallel. All right, one last example and get to my favorite part of the program after that. Given the points A, B, C, and D, determine if the line AB formed by those 2 points and the line CD are either parallel, perpendicular, or neither. All right, well, all we have to do is calculate each of their slopes independently and compare them. See if they're the same, see if they're opposite reciprocals, or some other combination would throw it into the neither category. So here we go. The slope of line AB. And I'm going to use the line as a subscript. So m sub line AB, that's going to be, again, my corresponding y values, 4 minus -2 over 1 minus -3. And that's going to be 6 over 4, which is 3/2. Rise over run, up 3 over 2. Let's go ahead and look now at the slope of the line CD. And using the CD notation as a subscript, I got my corresponding y values, -3 minus 3, over the corresponding x values, 5 minus -4. That's going to give me -6 over 9, which simplifies to -2/3. So I've got 3/2 and -2/3. Well, they're opposite signs, so they can't be parallel. But if they're opposite signs, they could be perpendicular if they're also reciprocals. 3 over 2, Flip it, you get 2 over 3, and they're opposite signs. So yes, these lines, they are perpendicular. If we had some other combination, if this was 3/2 and maybe -5/3 or anything other than -2/3, then it would be a neither. They would just be intersecting lines that don't intersect at right angles. All right, now it's time for the part of the show we call the Say What? And today we have for you a nice application courtesy of your federal government, namely the Department of Justice. This is from the American with Disabilities Act of 1990, which is basically passed to try to give equal access to all Americans, including those with disabilities, equal access into all areas. And that's specifically the example we're looking at today. Okay, now this is actually in the document. I got this from their website, and it's available at the bottom of the page here. But it's a pretty big document, so I had to comb through it to find this example. They have a section 4.7 that deals specifically with what they call curb ramps. And then a subsection of that is 4.8.2. And here's what it says. It says, the slope shall be measured as shown in the figure below. Transitions from ramps to walks, gutters, or streets shall be flush and free of abrupt changes. Maximum slopes of adjoining gutters, road surface immediately adjacent to the curb ramp or accessible route shall not exceed 1 to 20. Ooh, that last part really got my attention. 1 to 20. That's another way to write a ratio, 1 to 20. That's, if you look down here at the key, they're talking about the slope. See that? I'm zooming right in on it. They're saying the slope is y to x. So 1 to 20 is our slope. 1 to 20 means our slope shall not exceed 1 to 20. For every 1 unit of rise, we cannot exceed for every 1 foot of ride, we have to have at least 20 units of run. We can have more than 20. That would make the fraction smaller, but we have to have at least. Okay? That is a federal mandate there, folks. Okay? People in construction have to take this into account all the time. Here's their diagram, which kind of explains all their verbiage up here. They have a diagram, and they have y and x. Okay? Well, here's our scenario. We need to build a ramp to obtain access to a doorway that is 50 inches, which is really 4 foot 2 inches, above grade. Okay? So let's say we have a door that we need access to for everybody. We can't just build stairs because they're not wheelchair accessible. So we need to build a ramp. The question is, how long does our ramp need to be? How should we design it? Okay? If another ramp happened to be parallel with it, what would its slope be? These are all kinds of questions we can ask. What color is the ramp? Well, paint always comes last. Let's build this thing. We can set up a proportion here. The federal government mandates that we have to have 1 unit of rise per 20 units of run. Units. There we go. Well, I need to rise 50 inches. I'm going to do it all in terms of inches. So I need to rise 50 inches, and I'm trying to figure out what the run needs to be, how long it needs to be. So that would be, I'll call that x. Now if I cross multiply, I get 1 times x is x, and 50 times 20 is going to be this fantastic number, 1,000, and that's inches. Now that's not the tape measure distance along the ramp right here, along the slant. That's going to be this distance here, the horizontal distance. It needs to be 1,000 inches. In case you're wondering, 1,000 inches is approximately 83 feet, 4 inches. So just to get up to an elevation of 4 feet 2 inches, we need a ramp that will span at least 83 feet 4 inches. Well, that's going to take up a lot of space. If you've ever been out to Unicorn Stadium, right there at the entrance, you see that they actually have something that is about 4 foot 2 inches. It doesn't span 83 feet. So another design aspect that goes into this, if we're staring straight down at the ramp, we can actually build the ramp in multiple pieces. We can actually build it with a switchback where we come up this way, and instead of keep going, we can actually turn it, and then we can head back up this way. Now, believe me, that does get us in a tighter radius here, but there are all kinds of regulations about what that needs to be as well. So that would be another aspect of construction. But we at least know that the horizontal distance would need to be at least 83 feet 4 inches to pass federal regulation. So that's a pretty good application of slope. Oh man, that concludes today's lesson. I want to thank y'all out there for joining me on this fantastic mathematical ski trip we had today. I think I'm going to go inside the ski lodge and warm up with some coffee and do some more math problems by the fire. Until next time, I'm Kevin Corpy, and I'll catch you on the slopes and on the flip side.
You're watching Channel 98